So let's continue our look at quotient topology. Okay, so we define, so we've got the idea of a quotient space, a quotient map, and a quotient topology. It's sort of all sort of bound together. The basic idea, though, is you've got a space, then you make a quotient space on it by sort of identifying points in your base space. And so you sort of divide up into equivalence classes, and then you look at the set of equivalence classes. And so then the map that sends an element of X to its equivalence class, that's the quotient map. And then you have a quotient topology, which is the map induced by that quotient map, meaning that a set is open in your quotient space if when you pull it back, it's open in your base space. Okay, and so we've seen examples to show that subspaces don't necessarily behave very well under quotient topology. So just because you have a quotient space and you have a subspace that's saturated with respect to the quotient map. So that basically saying it's saturated basically says that the subspace kind of is compatible with the quotient map. Then you don't necessarily get a quotient map by restricting the quotient map to that subspace. But here is a couple of things which will ensure that that in fact does happen. So that if either the subspace is opened or closed in your space, or if the quotient map is either an open or a closed map, that will work. Okay, so the reason why that works is the following lemma. Again, so here we've got a quotient map, we've got a subspace that's saturated with respect to P. So remember what that means. That means that if you've got an inverse image of a point in the quotient space, that here, if one element is in there, then all the elements that go to that point are in there. And let Q be the restriction of that map to our subspace A, then it's always going to be true that the inverse image of any subset of the image of A is going to be, doesn't matter whether you look at it in the quotient map or the inverse image under the restriction map. And also image of U intersected A is equal to the image of U intersected the image of A for anything, for any subset of X. Okay. So remember, typically this inclusion only goes one way, but in the case where you go quotient map, that's always true. So this isn't saying anything yet about being Q being a quotient map or not. So why is that lemma true? Well, we've got that the image, since V is contained within P of A, that means the inverse image of V is contained within A. And since A is saturated, then both of these sets here, the inverse image of P and the inverse image of Q, are exactly those points of A mapped into V by A, so by P, so they're the same. The second one, we've always got this inclusion this way, that the image of the intersection is contained within the intersection of the images. Let's see why the reverse inclusion is. So let me give a new, let's see if I can work this. So let's say we've got some point in PU, what is it, intersection PA. Well, so let Y be an element of that. So Y equals P of U, and it equals P of A. So P of little u, that's some element of U, big U, and little a is some element of big A. Since A is saturated, so this is the reason why all these things work, we have that P inverse of P of A has to be in A. So that means in particular that little u has to be an element of A. So Y also, so that means U, this PU here, since U is in big U, we also see it's in big A, so therefore U is an element of U intersected A. And that gives us our reverse inclusion. Oops. Okay, so why is the theorem true? So it turns out that the proof for open and the proof for closed are the same. You just replace open by closed. So I only have to prove one of them. So let A be open, or capital A be an open set of X, or little p be an open map. What do we have then? Just trying to do things this way. So what do we want to show? We want to show that Q, so we want to show that Q is a quotient map. So that means, so Q a quotient map. So that means we want to show, given some V, right, in the image of A, we want to assume if Q inverse of V is open in A, then we need to show, so that this is, if this is true, then V is open in P of A. Right, so this is, we're restricting things to that subset A. Well, if A is open, the fact that Q inverse of V is open in A means then that means that Q inverse of V, then if it's open in A and A is open in X, then Q inverse V is open in X. And so remember that this equals P inverse of V by our lemma. So this means that P inverse of V is open in X, since they're the same set, right? So V is open in Y, and it's open in P of A, since P is a quotient map. So what happens if P is open? Then again, since Q inverse of V equals P inverse of V, we've got Q inverse of V open in A again. So we want to show that V is open in P of A. Well, P inverse of V is equal then to U intersected A. But what does it mean for a subset to be open in a subspace? Well, it means that it's the intersection of an open set with that subspace A. So where U is some open set in X. But P of P inverse of V equals V, because P is surjective. So we write down a whole bunch of equalities here. V equals this guy here, P of P inverse of V equals P of U intersected A, which equals P of U intersected P of A by the lemma. But this is open, right, because it's an open map. So that shows us then it's an intersection of open sets. So this shows that this is open in P of A, which is exactly what we're going to do, right? So this is an open set, and we're intersected with the subspace we're in. So this is an open subset of the space space P of A. It's open in P of A. Whew. Okay. Okay, what about other concepts? Well, the composition of quotient maps is going to be a quotient map, right? And that's because, let's try it on chalkboard, change. That's just due to the simple fact that P inverse of Q inverse of some set is equal to Q composed of P inverse of U. Okay, so this is the composition of two quotient maps Q and P. So we can pull open sets. If U is open, Q inverse U is going to be open, and then P inverse U is going to be open, and then you can go the other way because the map is composite. So because the maps are quotients. So you can just pull open sets back and forth between the two. And so composition. Other things actually are not so good. You've got to really work hard with quotient maps. We're going to show a really interesting example, which is kind of show you how groovy things can be. The Cartesian product of two quotient maps need not be a quotient map. Hausdorff, the quotient space of a Hausdorff space need not be Hausdorff. And in fact, it's really hard to come up with nice conditions to actually ensure that something is Hausdorff. An easier one is the T1 axiom. So remember, the T1 axiom is that finite sets are closed. All you need for a quotient map to be a quotient space to be T1 is for equivalence classes to be closed sets, right? Because equivalency classes get taken to a point, and so if you've got a closed set here, that tells you that that point is a closed set in the quotient space. So that's pretty straightforward. But of course, the really big thing that we always worry about is continuous maps. Okay, so what can we do to get continuous maps? Constructing continuous functions. So that's what we're going. That's the main thing we want to talk about today. So let's say we have a quotient map, and let Z is some other space, and we've got some function between x and z, and it's a map that is constant on the fibers of P, right? So it respects, it respects the saturation, respects the quotient map. Then this function here induces a map from y to z. So given a map from x to z and a quotient map, where y is the quotient space, then we have a map from the quotient space to z, such that the composition of that map with the quotient map is our function g. And it's continuous if and only if g is continuous, and it's a quotient map if and only if g is a quotient map. So this is the picture that we get. Right, so x, y, z. So where we've got a map going from x to y, which is our quotient map. We've got a map g going from x to z. And so what we're saying is then we can fill in the diagram with f such that this is a commutative diagram, i.e. that f composed with p equals g. Okay, so the first thing we have to do is we have to define what f is. We're going to make sure that f is well defined. Well, that's not hard because of the fact that it's constant on these fibers here. So we want to figure out, well, what is f of y going to be? Well, the thing is that if we look at g of p inverse of y, right? So we want to go f, right? We want to go from y to z. So what we can do then is take our y, we can pull it up to x, and then push it forward with g. And the fact that it's constant on this set here tells us that that's well defined, right? So that no matter which element of y we choose in this set here, it's going to be an element of x, and then we can pull that forward from x to z. Okay. So this is a single point, is the important thing I want to say. Since g is constant on that inverse image there, and so let that be f of y. So that gives us a well-defined map then from y to z. So if x is some element of x, x equals some p inverse of y, right? Because p is surjective. So g of x equals p of y equals f of p of x. Right, so if f is continuous, g is going to be continuous, right? Because then you've got just a composition of continuous maps here. Whereas if g is continuous, if we get some open set V in Z, G inverse of V, so we've got some V here, we can get G inverse of V here. If this is open, this guy is open, and then by the quotient map, we push it down and this is the same thing as what am I saying? G inverse V is open in X. That's equal to P inverse of F inverse of G of V. Yeah. What am I? So I'm saying, what happens if G is continuous? I want to show that F is continuous.
If G minus 1V is open, then P minus 1 F minus 1V is open.
Right. So we can say pull it down here with, since it's open here, this is going to be open here, and this is exactly F inverse of V. So V is open, it's open up here, we push it down, it's open here. So that means it was open if we just did it that way. And we can do the same thing. Same thing with quotient maps. What is it? F is a quotient map if and only if G is a quotient map. Well, if F is a quotient map, then G is the composition of two open maps. And if G is a quotient map, then G is surjective, F is surjective, and so you can do the same thing with what we did here, where you've got the open sets. You've got something open set here, you pull it back to open set here, you can push it down to an open set there. So the fact that G is a quotient map means you can put back and forth open sets here. You can put back and forth open sets here. And so since F is the composition, you can do the same thing with F. So that holds. So as a corollary from that, so if we've got like a surjective continuous map from X to Z, and you've got some sort of, let X star be the following collection of subsets, and so it's a quotient space, so you can give it the quotient topology. And so by up here, you induce a bijective continuous map. And that's going to be a homeomorphism if and only if G is a quotient map. But no matter what, if Z is Hausdorff X, the quotient space is going to be Hausdorff as well. And that's not so bad. It's clear that it's a bijection. So if F and P are quotient maps, right, then the quotient G is going to be a quotient map. And if G is a quotient map, then from the theorem, F is a quotient map. And so since it's a bijection, the fact that we've got quotient maps turns it into a homomorphism because both the inverse, right, is going to be continuous. So the only thing stopping a bijective continuous map from being a homeomorphism is if the inverse is not continuous. So the fact that you've got a quotient maps, meaning you can push open sets back and forward, means that we do have a homeomorphism. And why is Z Hausdorff? Well, if you've got distinctive points in X in the quotient space, what do we want to do? We want to be able to put neighborhoods around those distinct points, right? Well, the images under F are distinct because it's a bijection. And so since Z is Hausdorff, we can put distinct neighborhoods around the pre-images of those points. And then we just push them forward, and that gives us distinct open sets, distinct open neighborhoods in X star. So that has to be Hausdorff as well. So that's all good. So let's have a look at a couple of fun examples. So these are some examples of spaces. So this is kind of like a counterexample to the previous example. So this is an example where we have a bijective continuous map, but it's not a homeomorphism. Okay, so ignore these dots for a moment, and let's just consider the set X, which is the product space of the unit interval with the positive integers. So it's just a whole bunch of, it's a countable number of unit intervals sort of stacked one on top of the other. Okay? And let Z be, well, so what do we do? So we have, we've got sort of like the unit interval, and we've stacked it like this. So it's X cross X on N for different. So the main point is that when X equals 0, it's in the same point in R2. So these are both subspaces of R2. So here now we look at kind of getting unit intervals, and we give them that basically there's got slope 1 on N for all the positive integers. So sorry, slope, yeah, 1 on N. So this has got slope 1, a half, a third, a quarter, etc. And we get a point here. Okay. And so we get a map that goes from here to here by mapping a point. So what have we got to do? We've got a point in a unit interval, and we've got a positive integer. we then map it to the same point x in the first coordinate, and in the second coordinate we map it to x divided by n. So that maps it to a point somewhere in Z. And we're going to let the quotient space be then the inverse image of all the points in Z. So if Z is not the origin, there's a one-to-one correspondence with the points all outside here, which go to points here. But this point here, the origin, gets sent to all the starting points of the intervals here. Okay? And so we're going to let F be the map induced by G. Okay. So F is bijective, right? Just by construction, right? So the only point where G fails to be one-to-one is with the origin, and so we just squashed all those points into a single point. So we turned it into a bijection. It's a continuous map, right? So what are we going to do? So any open set here is going to go to an open set here, right? Because the only thing that's going to be any problem is going to be the origin, right? That the pre-image of the origin is going to be these points here. But if you have any neighborhood of here, it's going to intersect every segment, line segment. So it includes all the origins here, but it's also going to include some open start to every interval. So this map is going to be continuous. Okay. G is not a quotient map, though. And so because of that, F can't be a homeomorphism. So that means the inverse image of F cannot be continuous. And it's kind of easy to see why it can't be a quotient map, because the topology gets screwed up, right? So let's consider this sequence here, which is the sequence of points. What are the points? So let xn equal 1 on n cross n. Okay. So if we look at it in X, this is if we look at the set of xn's, it's a closed set, and there's no limit point. Right, because all the points are at least one unit away from each other. But when we look at the at G of xn, that changes, right? Because now these points this point gets to there, that to there, that to there. It's no longer closed set, right? Because 0, 0 is a limit point. And so we've got a sort of a topological property of these things, which is not preserved. So it can't be a homeomorphism. Here's an even more fun example. I really like this example. Oops. this is the one to show you that the product of two quotient maps is not a quotient map. So how do we reconstruct this? So let's start off with X being the real number line. And so then I want to consider the quotient space where we just identify the subset positive integers with the point Z. So what are we doing? So here is 0, and here is 1, and here is 2. So 1 and 2 are both positive integers. So what we've done then is we've identified 1 and 2. So we've got like a little loop like this. So 1 has to go back. The thing has to go back to 1 because 2 and 1 are the same. And then we go up again and we come back because 3 is a positive integer. So this is not a group thing, right? So I'm not saying that 1.5 is the same as a half, or, you know, they're 1.5, 2.5, 3.5, 4.5. Things that differ by Z are different because this is not a group thing. This is just the positive integers. So I'm just going around and around. And I just sort of go on forever. So this is between 1 and 2, 2 and 3, 3 and 4, 4 and 5. I just sort of go on forever. And so it's a crazy big earring that I've created. And so this is 1, 2, 3, 4, 5, 6, etc. So this would be 0, -1, -2, -3. Okay, so you understand this kind of guy? And so let P then be the quotient map that takes R, the straight line R. Is the quotient map that just sends it back to that point there. Okay? And so P is going to be pretty standard, right? So like it's identity on this section here, and it sends points, you know, here is between 1 and 2, so it just sends 1 and 2 to those points there. The only thing that's kind of fun is, well, what does a neighborhood of this point look like? So let's say, so what it is we just do, what happens if we do a little ball around here? Then in the real number line, right, it's going to be this infinite union of little intervals around each of the positive integers. Okay, and so that's a thing that goes crazy, obviously. So anything that goes wrong, it's going to be at this point here, right? So the only thing that's something unusual is going to happen. So let's go ahead and do that. So for our second space, let's just have Q, the rational numbers. And let I be the identity map that goes from, you know, just takes a rational number to itself. And so I want to consider P cross I. So this is a product of two maps. It's a product of two quotient maps, right? Because an identity map is trivially a quotient map. Right? Every point gets just sent to itself. Open sets are the same. So I'm claiming then that this is not a quotient map. Okay. And the reason why it's not is, let's have a look at the following thing. So this is X cross Q, right? So just think about, in this thing here, we've got real numbers, and in here, we've only got rational numbers. Right, so and this is a line above an integer. Okay, so in our space X cross Q is every rational number here, but every rational number along this line is the same, has been identified, every rational number line across all these lines, right? So you should think of those under this crazy thing here. This right has been glued to that, it's been glued to that, it's been glued to that. Okay? So let Cn be square root 2 divided by n. Now, it doesn't have to be square root 2, it can be any irrational number. The point is that Cn is going to be irrational for no matter what n you choose. Okay? And so there's Cn right here. And then we're going to consider the line of slope 1 going through there and the slope of line of slope minus 1 going through there, giving us a nice x. And so we're going to let un be this open set here, which is all the points that lie are either above both lines or below both lines and lying within a quarter. So this goes from goes from some number and 3/4 to some number and 1/4. Okay, so let that be un. That's an open set in X cross Q. Okay, so now the nice thing is, right, the reason why we chose Cn is that this line of rational points here lies entirely within the open set. Because this is an irrational point, it's not in un, but that's okay. We're only considering rational points being in un. So this is saturated with respect to P, right? So, and that's true for all the vertical lines here. Okay, so and let U be the union of UN. So of course, since this union N, I've got to watch my U's and my union signs. Do that. So this is going to be open. Right? It's just a union of open, it's an arbitrary union of open sets. And so what we're going to do is we're going to look at the image then of U under this product map. Okay, so remember everything, all these things, these lines get associated with each other, so they just get stacked with each other. And then the things that are not, it's kind of like you've got like, you know, what's that pastry, that Greek pastry, spanakopita. Have you ever had that? That flaky pastry where you've got kind of layers. You know what I'm talking about? So you've got these things which kind of just lay on top of each other, all kind of little layers. But you've got this central thing which is common, central spine, which is common to all. Okay. So what we want to show then is, if this was let's assume that this was a quotient map. If this was a quotient map, then this would be open in X star cross Q. So we're going to show that U prime is not open. And the reason why we do that is, well, we do know definitely one element of U prime, and that is this point Z, which is all the positive integers associated with each other cross 0. So this point here, is all the same point, and that's going to be in our set U. So if U prime is open, then it's open in the product topology. So what does it mean for a set to be open in the product topology? What's a basis element for the product topology? Open sets, right. So there's got to be some A cross B that contains, so Z plus 0 is an element of A cross B, where this is open in X star, and this is open in Q. Now, what do the open sets look like here? So that looks like intervals like, so it's centered at 0, so it looks like minus delta to delta, right? So this is this delta here. Okay, so we can choose an n such that the point Cn is going to lie within that delta. Right. What does the open set here looks like? Well, the open set here is just some W, it's just some neighborhood of this point here. We talked about, right, it has to be some neighborhood here, there has to be some little ball here that contains it. So what are we going to get a contradiction? Okay, so let's pull it back. So, and we get I inverse of minus delta to delta. Well, this is just the identity map, right? So this is just minus delta to delta. And so these sets here are going to be, let's call that V, what we've got. So this is what V is going to look like, right? It's going to be something between minus delta and delta in the horizontal direction, which is the rationals, and we need some neighborhood of the integers in this thing. So, but the thing is, of course, you see that if we choose n big enough, such that Cn on n square root of 2 on n is less than delta, then you can see straight away that there's points in V which is not in UN. And so that's a contradiction. So U prime can't be open. Right, V is not contained within this. There's no such neighborhood. So U prime cannot be open. So P cross I is not a quotient map. That's a pretty fun example, I think. Okay. And so just to set it up for the next class, I just want to talk a little bit about topological groups. So a topological group is a group that's also a topological space. But it's got to satisfy the T1 axiom. Okay, and it's got to do the group requirements, which are all, associativity, inverse, identity, closed under product, etc. And then the topological requirements are the T1 axiom, which means all finite collection points is closed, and the fact that the group operation and the group inverse are continuous functions. Okay. So if I've got a finite group, what's the topology on a finite group? Discrete. The discrete, right? Because every point has to be closed. So that means every point else is open since it's finite. And so everything is continuous. So finite groups are that. So we'll talk about this on Friday. It's just otherwise it's not interesting. So, okay, thank you.